Okay, well, he's got a question, and this is actually, number 3 is really the only hard one. The one, I can't remember, I think it's number 2, where you do the uncertainty principle. That's also, that's a good one to start with, because it's not hard. You're not integrating e to the sine of x or anything crazy. But you do get really, so direct notation is your friend with spin. It is your enemy when it comes to x, y, and z, unfortunately.
Yeah.
And so it just really gets awkward. And it's like trying to untangle spaghetti, right? So you know you can do it. It just sucks. So anyway, so you want to start with number 2.
Number 2.
And get your feet wet. Just get used to. I mean, you saw me do some proofs. You know, if I'm doing my job, I made it look easy. Then you try to do it, and all of a sudden, it's like a tangling spaghetti, and it sucks. But you figure it out.
Where you insert resolution and then each twice, right? X prime and the next double prime.
Well, now again, let me just not answer that because that's too easy.
Okay.
You have the momentum operator, and the momentum operator is defined. Okay, for the audience at home, number 2, remember these dashes are placeholders. That's their job. You notice that we have this definition. I think that might be, okay, now I've kind of forgotten. I know I'm doing this right, so either you're going to change all the dashes to double dashes, or you're going to change all the double dashes to dashes. It doesn't matter which one you do. It's not a big deal. Just make sure that it's consistent. So you really want to bracket your momentum operator because you've got a reasonable definition for it. So do what you have to do in number 2 to bracket your momentum operator. Now that clearly means that you're going to split the XD operator in 2, right? So you got in all the accompanying mess. So you're going to end up doing this. Sorry. What I did was wrong there, by the way. I forgot what was on the other side already. There's something here. Something there. I'll put it there. You do the same. No. See, I messed that up already. I already messed that up. Right? So you can do this, however. Notice I'm doing each side slightly differently.
Yes. That makes sense.
Now notice that when you, this one is really quite straightforward. The reason that you want to be careful about doing this, so for one, remember that the uncertainty principle, a commutator, is all about AB minus BA. So that's really straightforward here. Here you got to be a little extra careful. Here you can act on Lagrange. X is Hermitian, right? X position operator is clearly Hermitian because position is a real thing, right? So if it's Hermitian, let's act on the X double dash, right? So then what you get I already just messed it up. So there's your wave function. And so notice that, so the reason this is a little funky is that then this is going to turn into, I just don't remember what that would be, by the way. reality is, of course, there's actually two intervals here, right? So, the reason this is a little funky is that, again, you run into the situation of, this is an eigenvalue, so it's a number. But it's oddly not a number because I haven't really defined it, and it's in an integral. So this deal isn't just that deal, it's really this deal. You really got a product. You really got a product going on here. So anyway, so this is why it's a little fun. This problem is a little funny. Not only is it 10 miles long, you also have the same thing over here. You won't have a product rule over here because here you're going to get this. Again, I don't remember. And I'm just going to put that Dirac delta function somewhere convenient. Okay, so that's what you end up with. Yeah, it sucks. And then again, make sure that you're sensible. You know, which one are you going to wipe out? The x dash or x double dash? Looks like you want to wipe out x double dash here, mostly just because you bothered with this one here. And here, looks like you want to get rid of x dash because again, you've got this derivative. It actually doesn't matter. If you decide to get rid of x double dash, what happens is, if that's what you want to do, then those double dashes become single dashes. And that's gone.
Yeah.
And so is that. And look at that, I just did it. There you go. Okay, anyway, the question was number 3. Okay, well, now specifically, what about it?
So, first step, you want to show that the delta a squared, the operator delta a squared times b squared is equal to the square of delta AB inside the wave function. Broadcast notation.
What?
First, you want to show that. That's right.
Okay. Okay. What's a good way to begin this problem? Well, let's begin with what you're given, right? So, what is delta A operating on a? Let's start with the hint. So the hint is, okay, so you're given this. Right. Is that all you're given?
The information.
Information.
That's purely imaginary.
That is pretty, that actually is important. Okay, this. Now hold on, there's a little bit more there, right? It also tells you what else did I give you? There's some other
There's determination. You want us to show, you want us to prove the same structure principle and then show, you want to start here. Let's first show that.
Go down a little bit. Oh, okay, I don't remember how to do that one. Well, okay, so I guess I'm saying start here. All right, so now notice, what's kind of funky is I'm just writing that down, right? It's just, there it is. Notice the end goal is to turn this into what again?
The lowest possible result of the insertion principle, so it's 1/4. Do like commutator, any anti-commutator portion, that's right.
Okay, no, hold on, look at it. It says,
Or show that.
delta B, delta A. All right, now, so I want to do some reverse engineering. So what I would do is, let's make this look as familiar as possible. So again, I'm just starting there. I'm not setting it equal to anything. I'm just writing stuff down, spitballing. Okay, now what I need to do is be able to get a mixed. So I've got AA, B, B. And I'm not saying this equal to anything. I've just written it down. This is where this problem's weird. I've just written it down. Right? Then you're not kind of used to that. Usually it's equal to something, but. And I'll make it equal to something, but what am I going to make it equal to? Now notice that again, the end goal is that you're going to have an A and a B on the inside. Now here I've got an A and an A, and I've got a B and a B, but I've got to get an A and a B. I've got to mix it up now. And I'm also given this information, so what do I do? Okay, what do I do?
Start with insert identity somewhere.
All right.
Between two of the A's and then two of the B's. B's knows better.
I don't see that as productive at all. Why not give the information? And again, you want to have an A and a B inside, but here I've got two A's, I've got two B's, but somehow I need to replace them. Let's also not forget what this is. Again, look at what you're given. Knowing that you need to somehow get out an A and get out a B, how could you use what you're given to do that?
Start putting in,
Then
can we put in like, that second, you got the sine function. Yeah, can we put that into there?
No, I gave an identity for this, right?
you gave delta A. Okay, so you have delta B, delta L. So the first thing is that
Okay, what's the other one I have that I have?
psi, bra, delta A to lambda star, bra psi, delta B.
Okay, so I gave you all this, so now tell me, what's the first thing to do?
Insert you can insert lambda delta B psi down at the bottom left-hand side.
Lambda can go, it's just a number. Now what?
The same thing for the other side of delta B. On the right hand side, you have 1 over lambda. So you have psi delta B and then delta A psi.
Where's my lambda?
You could pull out in front, well, that would cancel, shouldn't it?
I just flipped over the first one. Relatively easy. It's not the hard part. Right?
Yeah.
And well, now at this point, you can kick into what I did in class, because the next thing is, sorry. It's important in the order, right? Look at that, it's a commutator.
So the AB cancels that and get delta B delta A squared is equal to, yeah.
Well, now this is actually gonna get, now I give you some hints, because it says, right, so when you square this, you get 1/4, right? So what's predicated on this working, so you're really almost home free. You've gotten here, part A done. If this is the square of that, then you are done. And then, of course, I already showed you that this is really, I did this in class.
Yeah.
So that's why I'm saying the lecture, I was even telling you that during the lecture, that the lecture was kind of essential for, and again, this is very trivial. So you guys show that 0. Now remember, in a big picture sense, because I don't have terribly much longer, I don't want to do too much. I mean, if I do any more, I'm doing the whole question. So let me stop there. But let me just point out that in class I showed you that this is Hermitian and this is anti-Hermitian. It's weird, but it's just like I just want that to be Hermitian because I'm used to that one. You rarely see anti-commutators. The only time I ever see anti-commutator is in this proof. But if it's Hermitian, and yet lambda is imaginary, those end up being incompatible. What you're gonna show is that those are basically incompatible. And the only way out is the null solution, 0 equals 0. So you can show that this is, you'll be able to show that this is 0. So the way you would do that is, let's make this. All right, so now you're working with this, and the problem is that there's no clear way forward. These are different things. They're out of order. So now you want to reverse engineer this. You want to put this back into order. You want this to be the same as that, and then you might add or subtract them. Hint, they're going to end up being subtracted. You're going to make them the same thing, and you'll succeed, except one will be the same thing minus the other thing. And A minus A is 0. That's how it's going to go. So in the big picture, though, this relationship, this imaginary relationship, is incompatible with a Hermitian operator. And I don't know how I can yeah, so it's like Hermitian operator eigenvalues are real, and so if I'm saying no, it has to have an imaginary value, you can't do both. The only thing that's imaginary and real at the same time is 0. That's kind of like, that's the best I can do in terms of like providing a big picture, and that's kind of half-assed, but it's the best I can do. Okay. How are we doing? I got 5 minutes.
Yeah. I didn't get past 3 of those. I was
The momentum problem is actually relatively easy. Now, I didn't cover it yet, but where you get thrown off is that you kind of have this.
Yep.
Now again, I'm just gonna, I'm just spitballing it. Now, the damnedest thing is, think about the beginning of the class, this bastard was a double derivative, and it made your life hell. Now, and then this thing just stayed by itself. Okay, now, what's kind of neat is that, again, nature doesn't see a difference between position and momentum. It is the same thing. And this problem, to be blunt, is rigged to be actually quite easy. Normally I look at this problem and say, holy donkey. But it's actually really quite easy if you choose to do it in momentum, because what happens is, just like x stays put, now p stays put. What x is going to turn into, actually I think it's minus, and again, I'm not writing this correctly, and there's some other terms, I'm just throwing this out there. What's kind of awesome about this particular problem is that it's not a double differential, it's a C. It's not a second order differential, which sucks. When you have a second order differential equation, you should cry. Those are impossibly hard to solve. This is a first order differential, which are the easiest diffies to solve. This is actually a really easy problem. But number 3, don't even worry about it. Once you get into it, and again, it'll help tomorrow. And I just gave tomorrow's lecture is, now I'm going to show you a little bit about the relationship between x and p in way more detail, other than, all right, momentum is a derivative look at what I did, sorry, you see what I did wrong? If p is ddx, x is ddp. That's what we're going to see tomorrow. Now I think one's plus, the other's minus, and I may be wrong about that, but anyway, so you get it. And so that's why this problem actually ends up being way the heck easier.
Sure.
What else we got?
The last one was the math.
Okay, that was actually kind of, the reason you had that question last time, the math question, is because of this one. I was actually just setting you up for this one. You already know the answer to this. It's almost the same problem.
Okay.
It's, right, I mentioned the uniqueness
Well,
theorem.
yeah, you wanna solve the derivatives.
Yeah.
Okay.
Now, the reason that you're doing that is, it's, now, you've been seeing this, let me use a Hamiltonian operator.
Sure.
Let me do that. Some other operator. You've been seeing e to the, let's throw an I in there. You've been seeing e to an operator, something e to the minus operator anyway. You're gonna be, on Friday, you're gonna be dealing with this. And guess what? This is the time evolution operator. So in many of your, if you get into any other quantum mechanical this or that in the future, you will often see the expression solved using that formula I gave there as a series of commutators where it's H. Yeah, it's really. Wait a minute.
Cover it up.
Okay, so what this is, by the way, yeah, just give me a second. What I'm gonna show you in the long term, now not on Friday, but on the following Monday, is that you can evolve a wave function over time, but you can actually evolve an operator over time. It's really a weird way to think, but this is kind of how we tend to do it. It's a little bit easier to do things this way. You can actually say that your state is static, and like the potential surface changes over time. You can. This is how we do it. Okay. Or actually, that's the time derivative. Is that what that is? No, sorry. So that's the thing. So it ends up being that the time derivative of an operator, which is a funky thing to think, ends up being related to this. I think I'm doing that right. Based on. Yeah, I have it right there.
Time derivative of the operator is equal to the
Yeah.
commutation.
So again, now we haven't really covered enough. So that question you can answer it on its own. But I'm just telling you, the reason I'm showing this to you is because you're going to get immersed in time-dependent quantum mechanics. We're going to spend quite a bit of time on time-dependent quantum mechanics. It looks like this. This is how you make an operator advance in time. And for various reasons, that's actually a really good way to do time-dependent quantum mechanics. So maybe you can do this, or another way to do this is to set up the time derivative of the operator, and then use this expression to solve for this. So you can do it this way, but sometimes you run into problems with this. It's like impossible. And so sometimes you do it this way. And the reality is, you can derive this from that, and that's actually part of that problem. That's actually what you're doing there.
Okay.
So again, I know that the question is kind of out of nowhere, but it's just, I'm just warming you up to see this and not like freak out